Alright, so we're going to talk about naming compounds now, and there's going to be several different types of compounds we're going to deal with. They're going to be covalent compounds, ionic compounds, and acids. What we're going to talk about right now is naming covalent compounds. Now, before we get into the naming side, we need to discuss some real basic stuff here first. You've got to recognize that when we look at the elements, those elements are going to combine together to make an infinite number of compounds. And we need to recognize that the properties of those compounds are going to be different from the constituent elements. That's why it's going to be important to be able to identify these compounds by different names as opposed to just simply looking at the elements they're composed of. So for example, if we look at hydrogen gas, it's got a boiling point of negative 253 degrees Celsius, which means it's a gas at room temperature and it's very explosive. Elemental oxygen, it's got a boiling point of negative 183 degrees Celsius, it's a gas at room temperature, and it's necessary for combustion. When we combine those two elements together, we can get water, which has a boiling point of 100 degrees Celsius, a lot higher than either of the other two, and it's going to be a liquid at room temperature. Hydrogen and oxygen can produce explosive conditions, combustive conditions, whereas water can actually be used to put things out. So what causes the difference in these properties? Well, what we have to consider is chemical bonds. So compounds are going to be made of atoms that are connected by these chemical bonds. It's what holds those compounds together. These bonds are going to be forces of attraction between these atoms, and there'll be different types of forces. But the main attraction is going to come from between protons and electrons in those atoms. We're going to worry about two types of bonds here. We're going to worry about ionic bonds, which are going to be formed from metals combining with nonmetals. And we're going to worry about covalent bonds, which are typically formed from nonmetals combining with nonmetals. So water on the left is going to be a molecular compound because it's formed from the nonmetals hydrogen and oxygen. It's going to form covalent bonds. On the right, we have sodium chloride. That's going to form from sodium metal and chlorine gas. That's going to be an ionic compound. We've got sodium metal, chlorine's a nonmetal. We're going to have that ionic bond formed. Now the properties of these two are quite different. If we look at water, water is a liquid at room temperature. If we look at salt, it's a solid at room temperature. The reasons for that involve in part those bonds between those atoms. So understanding whether we're dealing with a molecular compound, which is formed from nonmetals, has covalent bonds, or whether we have an ionic compound, which is formed from a metal and a nonmetal, and that metal and nonmetal form an ionic bond, it's going to be important to distinguish between those. And it's going to be very important when we get to our naming rules, because we're going to have different types of rules for these different types of compounds. Let's look at covalent compounds. Covalent compounds are going to be formed from nonmetals. So a nonmetal combining with a nonmetal. Remember, nonmetals are going to be on the right-hand side of the periodic table. Metals are going to be on the left-hand side, and the metalloids are going to be between those two. So you need to be able to recognize where the metals, metalloids, and nonmetals are at on the periodic table. We're going to form covalent bonds by actually sharing electrons. We're going to see this mostly in what we call molecular compounds. So you're going to hear me say molecular, covalent. Those are going to interchange quite a bit. Okay, so I just want you to be able to recognize those. So let's look at two atoms of hydrogen. Hydrogen's going to have one proton, one electron. Protons have a positive charge, electrons have a negative charge. Well, positives and negatives attract, so as those atoms get closer and closer together, the protons from one atom start to attract the electrons from the other atom, and vice versa, until they get close enough where they actually share each other's electrons between them. That's what makes up a covalent bond. Now we have to worry about all the forces combined together. So while we have the attractive forces between the protons and electrons, we're also going to have repulsive forces involved, where the protons, as they get closer and closer together, they're going to repel each other because they have the same charge. And as the electrons get closer and closer together, they're going to repel each other because they have the same charge. So it's this balance of those repulsive forces and those attractive forces, and as long as the attractive forces can overcome the repulsive forces, we're going to form a bond. This bond then, because they're sharing electrons between the two atoms, that's going to be a covalent bond. Once we know we're dealing with a covalent compound or a molecular compound, if you will, we then use a certain set of rules to name that compound. Now we're only going to worry here about binary molecular compounds. Binary molecular compounds are going to have 2 elements. Okay, so keep that in mind. So we're going to worry about 2-element molecular compounds for this. One thing to keep in mind as you're writing names and as you're writing formulas, typically the most metallic element is going to be written first. So if we look at the periodic table, metals are on the left-hand side of the periodic table, so as we go across a row, we get more metallic as we go to the left. What about down a column? Well, if I look at 4A, it starts with carbon, ends with lead. Well, carbon's a nonmetal, lead is a metal, so as I go down a column, I get more metallic. Okay, so keep that in mind. Typically, the most metallic one is written first. There are a couple of exceptions. We can have NH3, where nitrogen comes before the hydrogen, and then oxygen. Whenever we have oxygen, oxygen is going to be written last. So, as I stated before, if both elements are in the same group, the lower one is written first, because remember, in that group, in that column, the lower one is going to be more metallic. With the names then, the name of the second element is going to be given an IDE ending. And then we're going to use Greek prefixes to indicate the number of atoms within this compound. You should know the Greek prefixes for 1 through 10, so make sure to look at those. When it comes to names and formulas for these compounds, the most metallic element gets written first, followed by the second one, except for oxygen. Oxygen is always written last. Okay? Then when we go to actually write out the entire name, we need to use Greek prefixes to indicate the numbers of them, followed by the name of the first element, the most metallic element. And then we use the Greek prefix to indicate the number of the second element, and we use the base name in that second element plus the IDE ending. So let's look at some examples of these. If I start with Cl2O, first off, whenever you're looking at these compounds, you need to identify, am I dealing with a molecular compound, am I dealing with an ionic compound, or am I dealing with an acid? Because that's going to determine what types of rules you're going to use for the naming. So always look at that. So in this case, chlorine's a nonmetal, oxygen's a nonmetal. They're both nonmetals, hence we're dealing with covalent bonds, molecular compounds. Okay, so we're good to use these naming rules with this. Okay, so Cl2O, well, we have 2 Cl's, so we'd start with di, that's a Greek prefix for 2. Name of the first element, well, Cl represents chlorine. Then we go to the second element. We have 1 of those, so it would be mono. Mono is Greek for 1. We take the base name of the second element being oxygen, so we drop the end off of that and add an IDE, so we end up with oxide. When we put it all together, we get dichlorine monoxide. Now if you notice, whenever I'm dealing with the oxygen, I don't want to write monooxide. I didn't put 2 O's. I drop one of those O's and just write monoxide. If I'm dealing with something other than oxygen, I'll keep the MONO, I'll keep that O. If I'm dealing with oxygen, I'll drop that extra vowel. Alright, let's look at the next one here. We've got NBr3. So N, we have 1 of those, so it's mono. N stands for nitrogen. Next we go to Br3, we have 3 of those, so that's tri. Okay, Br stands for bromine, so we drop its ending, add IDE, so we end up with bromide. Put it all together, and we get nitrogen tribromide. Now wait, what happened to the mono? Well, it turns out if you only have 1 atom of the first element, you don't need to include that mono. So we don't write mononitrogen tribromide, we just write nitrogen tribromide. Because when we see that nitrogen without a Greek prefix, we know there's only 1 of those. Okay, so if we have mono for the first element, we don't need to include that. If we have mono for the second element, though, we always need to include it with that second element. Another example, N2O4. So it's di, nitrogen. We've got 4, which is tetra, and it's going to be oxide. So we get dinitrogen tetroxide. Notice, I didn't write tetraoxide. I dropped that extra vowel. In this case, it's an A, so I just put tetroxide. Once again, I'm only doing that with the oxide. All right, let's look at another example. CCl4. So we have 1 C, so it's mono. C stands for carbon. We have 4 Cl's, so it's tetra. Cl stands for chlorine. We drop the ending, add IDE, we get chloride. So we end up with carbon tetrachloride. Again, look at the A. I didn't drop it for that. I only dropped it because of the oxide part, so I didn't have two vowels together. A couple more examples here. CO, we've got mono, carbon, mono, oxide, so I get carbon monoxide. Remember, I don't include the mono if I only have one atom of the first element. S2Cl2, so it's disulfur dichloride, so disulfur dichloride. P2O5, diphosphorus pentaoxide, so diphosphorus pentoxide. We've got ICl5, so mono iodine, pentachloride, so iodine pentachloride. Okay, so you get the idea of how to write names from the formulas. Now we do need to be able to work this backwards and go the other direction. We need to be able to write the formulas from the names. Well, it turns out with covalent compounds, it's relatively straightforward. So if we look at xenon hexafluoride, well, I just need to know the atomic symbols for the elements and how many of each I have. Well, xenon is Xe. I don't have a prefix with it, which means I know it's got to be just one of them. I've got hexafluoride. Well, fluoride, it's going to be coming from fluorine, so that's F, and I have hexa amount of those, which is 6. So my formula would be XeF6. Look at phosphorus pentachloride, PCl5. Dibromine heptachloride would be Br2Cl7. And the last one, tetrasulfur pentoxide, would be S4O5. So when looking at naming covalent compounds, remember, covalent compounds are going to be nonmetals combined with nonmetals. And then with the rules, we're going to use Greek prefixes. We're going to use a prefix, name of the first element, prefix, and then the base name of the second element plus an IDE ending. And really with covalent compounds, in the name we're told how many of each atom we have. Naming covalent compounds is actually relatively simple compared to the next ones we're going to talk about, which is naming ionic compounds and naming acids. That's going to be it for naming covalent compounds.